A modern cargo ship is essentially a floating city, and just like a city, it has an immense daily thirst. Between the crew's drinking water, showers, and the thousands of liters needed just to keep the ship's massive boilers running, the demand for fresh water is relentless. A ship cannot simply fill giant tanks at a port and carry months' worth of water. The math doesn't work. Storing those thousands of cubic meters would take up valuable space that needs to be filled with paying cargo. Since the ship is surrounded by millions of square miles of ocean, the most straightforward answer seems to be pulling that seawater in and boiling it to create pure steam. But bringing millions of liters of water up to 100 degrees Celsius requires burning a prohibitive amount of extra fuel. The cost of the energy alone would make the voyage commercially impossible. There is also a hidden chemical cost. Heating seawater to 100 degrees causes the magnesium in the salt to form magnesium hydroxide, a rock-hard scale that quickly coats the inside of the pipes and restricts the flow of water until the system fails. This creates a difficult operational constraint. The ship needs to boil seawater to survive, but it cannot afford the fuel cost or the mechanical damage that comes with reaching 100 degrees. Marine engineers solve this by manipulating the physical environment inside the ship. They use a system called the freshwater generator, relying on a principle known in the engine room as pressure cacale. The system relies on a specific rule of physics. The boiling point of a liquid is tied directly to the ambient pressure. If you decrease the pressure on a body of water, the temperature required to make it boil drops immediately. If you seal seawater in a chamber and pull the pressure down until it's nearly a vacuum, the boiling point plummets. Instead of requiring a furnace to hit 100 degrees, water in a near vacuum state will violently boil at just 40 to 50 degrees Celsius. In this environment, you could comfortably touch the outside of a boiling pipe. By artificially creating a vacuum, a ship can boil thousands of liters of seawater, using heat that would normally be too low to even make a cup of tea. This schematic shows exactly how the freshwater generator executes this pressure-based strategy in a continuous closed loop. At the bottom right, the ejector pump and the air brine ejector initiate the process. These ejectors suck air out of the main evaporator shell, maintaining a massive 90 to 92% vacuum monitored by the gauge at the top. Under this intense vacuum, incoming seawater boils at just 50 degrees Celsius. To provide heat, the system uses what would otherwise be wasted. On the left, the main engine jacket cooling water line flows into the evaporator block. This water sits around 80 degrees Celsius from cooling the engine cylinders. That thermal energy flashes the 50 degrees seawater into steam. As the vapor rises, it passes through a demister, catching heavy, salty droplets. The pure steam then enters the condenser block at the top, where cold seawater cools it into liquid. Before reaching drinking tanks, a salinometer tests the batch. If salt content exceeds 10 parts per million, a solenoid valve dumps the water overboard. The ship efficiently uses waste heat to manufacture this vital resource without spending a penny on extra fuel. In the grit of a ship's engine room, the freshwater generator requires constant monitoring. It is a sensitive balance of pressures and temperatures that marine engineers must manage every hour of a watch. While operating at 50 degrees avoids the rock-hard magnesium hydroxide scale that appears at higher temperatures, the plates are still prone to mineral buildup. At these lower boiling points, the seawater still leaves behind calcium carbonate. Over time, this coats the titanium plates of the evaporator and slowly chokes off the heat transfer efficiency. To prevent this, engineers continuously dose the incoming seawater with chemical treatments, like VapTreat. This keeps the plates clean and ensures the vacuum remains stable. A cargo vessel is effectively a self-sustaining island, disconnected from the rest of the world for weeks at a time. The next time you see a massive vessel on the horizon, remember that the crew survives not on stored water, but on pressure cacale, a manipulation of physics that turns a problem like waste heat into pure life.